A problem? Well, because TSID is a control framework. So you want to solve it, you want to solve the quadratic program at each iteration of your control loop. And typically, if you're controlling a legged robot, or actually almost any kind of robot, you have a very fast control loop, which means you have a limited computation time. The range is usually between 1 and 10 milliseconds. So I typically try to do it in 1 millisecond, so that's my goal. We need to solve the TSID quadratic program in less than 1 millisecond, because if you have 1 millisecond for the whole control loop, of course TSID needs to take less than that. So how big are these quadratic programs that we need to solve? So in terms of number of variables, we have the number of degrees of freedom plus the number, which are accelerations, the number of control inputs, the joint torques, plus the number of contact forces, because we're talking about a robot that is in rigid contact with the environment, so the contact forces are part of the problem variables. And we get to about 70 for an average humanoid, let's say. Then you have also equality constraints that play a role in the computation time. You have the equality constraints for the dynamics and the equality constraints for the contact constraints, because contact points do not move. That's a constraint. That's about 40 for a humanoid. And then you have inequality constraints on the accelerations, on the joint torques, and on the contact forces, where you linearize the friction cones. Here the assumption is that you use a four-sided pyramid for linearizing the quadratic friction cones. And this is a number that is roughly close to the same as this, so around 70 or even 80. Okay, how complex is that? A QP with 70 variables, 40 equality constraints, and 80 inequality constraints. Well, in theory, the computational cost of a quadratic program, to answer your question, Johan, is dominated by the decomposition of its Hessian. So the Hessian is an n by n matrix, where n is the number of variables, so around 70 in our example. And this cost is proportional to the scales with the cube of the number of variables. Okay, interesting. The question is, can we solve a problem with this size in less than 1 millisecond? And if not, there is a way to speed up the computation to make the problem faster to be solved. And actually, this has been a very active research topic since a few years ago, and many people have been working on trying to reformulate this optimization problem so as to make it more efficient. And today I want to show you what I think is the best solution that has been proposed, which is the one that's also implemented in the library we will be using later. And we will be quickly discuss the other approaches and why I think they are not worth your time. So the key idea is always the same. We have an optimization problem, we want to make it faster, and if you have taken some classes about numerical optimization, you will know that there is only one way to make an optimization problem faster to be solved, that is to exploit the structure of the optimization problem. Because if your problem has no structure, there is no way you can make the computation faster in general. So we can take a look at the equality constraints of our problem. And here you can see that I have decomposed the dynamic constraint that previously I represented as only one line. Here I decompose them in two lines. You have the under-actuated dynamic and the actuated dynamic, as we had seen in the beginning of the lecture. And you can see here in red there is a very special matrix, which is the identity matrix. And the identity matrix is really nice because it's quite easy to invert, right? The inverse of the identity is the identity itself. So what does it mean in practice? It means, since we have the identity there, this corresponds to the joint torque, because this multiplies this. It means that we can easily express the joint torques as a function of the other variables, because to compute tau from the other variables, we need only to invert the identity matrix, which is effortless, it costs nothing. So we can express the original problem variables very easily as an affine function of the new problem variables that are the same without the joint torques. So we can easily remove the joint torques from the variables of our problem, and this costs basically nothing because we don't have to invert any matrix. This wouldn't be the case if we were trying, for instance, to remove the accelerations or the forces, because in those cases we would need to, for instance, for the acceleration we need to invert the mass matrix, and that costs something. So in practice it's not really worth it. But for the torques, it's worth it. So you express the original variables as an affine function of the new variables, but how does it affect the optimization problem? So this is the original problem. We have the least square cost function, we have some inequality constraints, and we have the dynamic of the system, which are the equality constraints. So if we use the previous expression to express the original variable as a function of, as a linear function of the new variable y bar, which are just the acceleration and the forces, we can easily plug this inside that problem, and we get this new problem where we have much less variables because we no longer have the joint torques, and we also have less constraints, because if you plug this inside the last constraint, you get 0 equals 0. So that's a constraint that is always satisfied. So we got rid of NA constraints, where NA is the size of the joint torques, and NA variables. So we just made the problem much smaller, and hence much simpler and faster to solve. It's a very simple trick, but it took our community many years to figure this out. Make us look a bit dumb. That's how it goes. The best ideas, once you have explained them, they look so simple that you cannot see why people didn't think of that before.
So NA is roughly the half of the problem?
It's like roughly 30 in my example before.
Okay.
So, I don't know. Yeah, in the example before we went from 70 to 40.
40. Mm-hmm.
And the constraints, we went from 40 to 10, 15. So it's a big cut in the number of variables. And since the complexity of the problem was cubic in the number of variables, that's an improvement of a factor 8, not a factor 2. It's 2 to the power of 3. So the question is, can we improve even more? And in theory, yes, there are ways in which we could improve even more. And here are just a couple of examples. We could also remove the first 6 variables of the accelerations, exploiting the structure of the subpart of the mass matrix corresponding to those variables. Okay, we're going in very technical details. Or we could remove some or all of the force variables we don't care about, but I cannot think of any case in which we don't care about the force variables, because we always care about the contact forces we are applying on the environment. at the end of the day, you could use these tricks to make the problem even more efficient, and you can find plenty of papers discussing in details how to do that. But you are either accepting to limit the expressiveness of your problem, because if you remove the force variables, you cannot have constraints on the contact forces, you cannot have a cost function of the contact forces, so you're just leaving the contact forces to be randomly chosen by the solver, which is not a good idea. Or you're accepting a higher complexity of your software implementation for a very small improvement in performance. So my personal opinion, not worth it. So I suggest you not to do it. And I didn't do it when I had to implement the library for TSID. So yeah, one small note. So far, we have assumed that our task functions are expressed in an Euclidean space, so we can nicely represent everything with vectors in Rn. But as you have seen yesterday with Nicolas, if you want to represent the placement of a body in space, that's not an Euclidean space, that's a Lie group, unfortunately. So how do you generalize what you've seen so far to make it work on Lie groups, especially in SC3, because that's the Lie group we care about the most? There is one little thing that you have to change, you need to be aware of. Apart from that, it's basically the same. So for representing SC3 elements, we can take the classical approach of using homogeneous matrices, which are 4 times 4 matrices. We have rotation, translation, 0, 1. And you need to redefine the error function, because you can no longer take the difference between the two homogeneous matrices. That doesn't make any sense. You have to use the log, which is the pseudo-inverse operator of the exponential map, which is the metric exponential in the specific case. So if you're going to look through the code of TSID, you will see that when computing the error of an SC3 task, there is a call to the function, to the Pinocchio function log, which computes this operation. That's the only small difference. It doesn't make a big difference at the end of the day, but it's nice to be aware of that.
Why do you call it pseudo-inverse and not inverse?
I'm not completely sure of why it's not exactly an inverse operator. The reason I did it is because that's how it's defined in Pinocchio's documentation. I don't know the theoretical reason behind that. Maybe Nicolas does.
I'm not sure what you are meaning by not exactly.
It's the inverse up to.
Just explain again what you say that.
I said that I took that from the documentation of Pinocchio.
And what's wrong in that?
Why it's pseudo-inverse and not exactly inverse?
Oh, because
I guess it's not always invertible depending on the matrix.
Because of the modulo pi?
Probably it's the only thing.
Okay, because of the modulo pi.
Yeah, okay.
Okay.
But I would say reciprocal rather than pseudo-inverse. Pseudo-inverse is
Then you should update the documentation of Pinocchio.
okay.
Or
No.
Justin should.
It's mostly unimportant, but pseudo-inverse can lead to.
Yeah, it's not a
matrix
pseudo-inverse.
pseudo-inverse, and
Yeah, it's not the pseudo-inverse of a matrix. It's a different.
Is brand. It is owned by Moore and Penrose.
Yeah.
Okay. Okay, then you have some references and some historical notes, which I will skip. And we can move to the second part. So far we have seen the theory. Now let's move on to the implementation. Before I let you play with the software, by the way, how is it going with the software installation? Is everybody able to run the examples?
I didn't which example?
In TSID you have a directory, exercises. Inside that directory you have 2 exercises, x1, x2. You can try to run those. Those will be the starting point for the lab.
So if I already passed the test formulation script, is okay? Or?
Yeah, it's very similar, so it should be okay. Test formulation doesn't use the viewer.
Yes, but there is a demo of Romeo.
Demo Romeo, that one, it was my starting point for doing the exercises. So if that works, everything should be fine. Yeah. So was anybody unable to make the example work? Okay, you. Okay, well, sorry about that. But 1 out of 30, I'm impressed.
No, the point of CRI is unacceptable.
Okay, before we start playing with the code, I need to explain a little bit how the library works, because otherwise you're gonna be lost. But I will try to make that as fast as I can. So TSID, it's a library that implements the TSID control framework. Surprise, surprise. It's a C++ library. It's open source. You can see the source code on GitHub. And its main dependencies are Eigen for linear algebra, Pinocchio for multi-body dynamics, and A-quad-prog for solving quadratic programs. Just so you know. So, very quickly, what are the pros and cons of this library? Let's start with the cons. So it's nicer to finish with the pros. The library is not very mature in terms of software. It's not as mature as Pinocchio, for instance, which is 5 years old, I think. TSID is only 2 years old. And it doesn't implement all the features that we have seen before in the theory. And these are maybe features that you need for your actual application. So for instance, it doesn't implement a hierarchy, you only have soft priorities. It doesn't work with fixed base robot. It assumes that your robot has a floating base because it was designed to control legged robots. It doesn't implement joint position velocity limits, actuation limits, bilateral contacts, which are not very common, but you may want to use them, or line contacts, so when you have a contact with a line contact surface, and many other things you may want to do. So it doesn't look that great starting with the cons, but now let's see the pros. It's very efficient. That's not thanks to the library itself, it's mainly thanks to the dependencies of the library. So we use Eigen for linear algebra, that's very efficient, Pinocchio for dynamics, that's very efficient, and A-quad-prog for solving the QPs, that's also very efficient. I think we're using the best of any subject in terms of implementation. That's why it can be so efficient. For instance, for running it on a humanoid, it takes less than 0.6 milliseconds. So it's well below the bars that we set before of 1 millisecond. It has been tested both in simulation and on a real robot, HRP2. Maybe they're also using it on Talos, I don't know. And there are people using it around Europe in certain labs. I'm not completely aware of who is using it. It's open source, as I said before, so you can look at the code. And more importantly, it has been designed in a very modular way, which should make it quite easy and straightforward to extend. So it's true that many features are missing, but it's also true that you can quite easily extend it. It's not like Pinocchio. Pinocchio, it's a mess if you want to extend it, because the code is written in a very particular way, which makes it hard to read and to write. TSID is written in plain and simple C++ object-oriented style. So it's a code that I think you can easily read. It is more or less documented, now more thanks to this class I had to prepare. And also many of the features that are missing, like all of them except the first one, are very easy to do, to implement. Probably I could implement any of these features in a few hours. So if you tell me, I would really like to use TSID, but I need this feature, I can probably implement it within a few days. If you don't dare going inside the code and implementing it yourself. Another big advantage is that you have Python bindings, not thanks to me, but thanks to a student working at class who took the time to do that. And this is not really a pros of the library, but it's good to know. I'm not aware of many alternatives if you want to do task space inverse dynamics. I'm not aware of any other library that implements this in C++, so that's efficient enough to be used for real-time control. So you have no choice, you have to stick with that. So let's quickly go through the key concepts of the library so that you're not completely lost when you see the code. They're very similar to the key concept I explained in the theory, but just to recap. We have the concept of a task, which is an objective for the robot. We have motion task, force task, actuation task. That's almost the same taxonomy we went through for defining the task function, except that now we have also the force case, because we consider robots that are in contact with the environment. So motion task is move my end effector or move my center of mass. A force task is I want to apply this contact force on the environment. An actuation task is I want to minimize my joint torques, for instance. Then we have the concept of a rigid contact, which is kind of similar to the concept of a task. Also in theory it was similar, but the main difference is that when you introduce a rigid contact, you're also introducing reaction forces, which is not the case when you're introducing a task. There are no forces, reaction forces associated to a task. Then we have the concept of inverse dynamics formulation. This is kind of the core class of the library. It's a class that basically collects all the tasks and all the rigid contacts of your problem and translates them into a quadratic program. It's similar to the transcription that you have to do in optimal control, basically. That's the class that takes care of the transcription. It starts from this abstract high-level specification of your control problem, and it transforms it into an optimization problem that a generic QP solver can solve. Okay? And this is where you need to decide how you want to formulate your optimization problem. And here the one formulation that we implemented was the one that I explained 5 minutes ago, where we remove the joint torques from the variables of the problem to make the problem smaller, hence faster to solve. So HQP means hierarchical QP, because even if the library doesn't implement a hierarchical solver, the interface is the one of a hierarchical solver, because the idea is that one day we may implement a hierarchical solver. So at the moment you can only have 2 levels in your hierarchy, which are the constraints and the cost function. And then you have the concept of HQP solver, which solves a HQP, simple enough. And another few concepts that may be important, you may encounter when you're reading the code. You will encounter some objects that are called constraints. These are not rigid contact constraints. Constraints in the library are purely mathematical functions that are not aware they are being used in a robotics context. So constraints are a affine functions that are used to represent a hierarchical QP. So a hierarchical QP, we will see it later, it's just a collection of affine functions which we call constraints inside the software. Then you have the concept of a robot wrapper, which probably was introduced by Nicolas yesterday. If you have played a bit with Pinocchio, you have played probably with this class robot wrapper, right? Or no?
Yes, on that. I'm using in the class I use robot wrapper like you are doing as a display.
Okay. Okay. Well, anyway, it's an abstract interface of the robot. It provides you method to compute the quantities that you need to formulate TSID. So there is a method to compute the Jacobian, a method to compute the position of a body of the robot. We have a method for computing the mass matrix, the bias forces, a method for computing the velocities of all the bodies, the center of mass, all these kind of quantities that you need to compute. Those are provided by the robot wrapper. And at the moment, the only implementation available for the robot wrapper is using Pinocchio, but in theory, if you prefer to use RBDL, you can write a new implementation of the robot wrapper that computes all these quantities using a different library that is not Pinocchio. To be honest, I see no reason for doing that, because Pinocchio is the fastest library I'm aware of. But if you're really attached to another library, you can do it. And then you have the concept of trajectory, which shouldn't be complex. It's just a mapping from time to vector values. And the only important detail is that position and velocity of a trajectory can have different sizes, and this is necessary to work with SE3. For the position, we have for the orientation part, we use quaternion following the choice of Pinocchio. So details, yeah, we're going to see a bit more in detail what each class is doing. Let's do this very quickly. So the robot wrapper, as I was explaining you before, it has this important function, computal terms, which actually maps the Pinocchio function, computal terms, which computes basically everything you need. So you call that, and then you have just this nice method for getting the quantities that you want to get for formulating your problem. So center of mass, mass matrix, positional acceleration, and Jacobians. So constraint, as I was saying, constraint is not a contact constraint. It's simply a linear affine function, purely mathematical. And we have three kinds of function: equality constraints, inequality constraints, and simple bounds. The reason why we introduced simple bounds is that some QP solver are able to work with simple bounds in a way that is different and more efficient, and they handle inequality constraints. So it may be worth to make a difference between these two cases, because this one is simpler than this, and in practice this is very, very common for TSID. Okay, well, the interface, not really exciting. Then we have the concept of task. Again, a simple control objective. We have three kinds of task: task motion, task contact force, task actuation. I guess by now you can guess what they mean. Tell me if that's not the case. So each task can either compute an equality constraint, an inequality constraint, or a bound. So example of task computing equality constraints are task COM equality, so for controlling the position of the center of mass, task joint posture for controlling the joint posture of the robot, and task SE3 equality if you want to control the placements of one link of the robot in space. When you have bounds, one example would be task joint bounds or task actuation bounds, if you want to specify bounds on the joint torques, for instance. Those are not implemented, but I can add them if you want. And then you have inequality constraints, such as the friction cones or the contact forces. Those are the only ones that are implemented. Then we have contacts, and this is the only complex part of the library. And this is where I need to take a bit of time to guide you through the choices that we had to do when designing the library. So, a contact is a bit more than a task, because when you're introducing a contact, you're introducing also contact forces that are associated to the contact. And you're modifying the dynamic of the robot, which is not the case when you're specifying simply a task. And these are the main methods of the class contact. And I want to go through each one of these 4 methods, not counting the constructor, to explain to you what a contact implies. So the first method is compute motion task. And this represents a motion constraint that is introduced by the rigid contact. So contact point, don't move. This is represented by the motion task. And this will be added as a constraint in your quadratic program. And as Antonio was pointing out before, we account for having a feedback term, because if you're doing simulation and you don't have these feedback terms, you might have a drift due to numerical issues, and your contacts may actually move even if the acceleration is 0. And the second function is compute force task. The first task represents the inequality constraints that are acting on the contact forces. So the only case that's implemented is for friction cone constraints. And those will also be added as constraints in the quadratic program. And the third concept is force regularization task, because typically when you introduce contact forces, sure, you want them to stay inside the friction cones, but typically you want them also to stay as far as possible from the boundaries of the friction cones. Because if you get close to the boundary, then your robot might sleep. And typically you don't want that. It's very hard to control a robot that is sleeping. So you achieve this by adding a cost function on the contact forces. And this is called the force regularization task, because it regularizes the contact forces according to some affine functions that you specified. It's actually a quadratic function. And now this is the tricky part, because this is something that we didn't talk about when discussing the theory, and is something that you rarely find discussed in papers about TSID.
I'm sorry, I just have a question. So, I mean, the friction constraint should be able to somehow save me. So if I have it completely satisfied, I should not need regularization of the contact forces, right?
In simulation, indeed, you don't need. On a real system, since all models are wrong, you won't have exactly the contact forces that your solver has computed. You're going to have some errors, right? So you don't want your contact forces to be exactly on the boundary of the friction cone, because if that's the case, you're going to sleep most probably. And the force regularization task can help you in this case. But it's true that for simulation you don't need that. Maybe later you can try, you can disable that task, and you see that nothing will change. But on a real system, that's important. That's really, really important. So, Yeah. The last concept that's really important for understanding the library is this force generator matrix. So the force generator matrix, let's call it capital T. It's a matrix that maps the force variable to the space in which represents the motion constraint. So typically, these two spaces are considered to be the same. And this is actually connected to the remark that Johan did before, that the Jacobian used for the motion constraint is the same Jacobian that maps the contact forces in torque space. And that's true if you're representing forces and motion in the same space. Let's take, for instance, SE3. So your motion is represented as a twist, so it's a 6-dimensional vector. And your force is represented as a wrench, which is another 6-dimensional vector. And in that case, you have the same Jacobian. But we're going to see in the next slide that there might be a good reason for not having the same space for representing forces and motion. And in this case, you need to have a matrix that is mapping between these two spaces. And this matrix basically goes to modify your Jacobian when you use it to project the forces in the space of the joint accelerations. But you can see it doesn't appear here. It appears only here. So what is a good reason for adding this complexity to the library? Let's consider the case of a unilateral plane contact. So you have your foot on the ground. It's unilateral because I can only push, I cannot pull. It's only one direction. And it's a plane contact because it's not a point, it's a plane. So my foot cannot move in any direction, neither can it rotate. So you have a 6-dimensional motion constraint, no motion allowed in any direction. So as I said before, the minimal representation for the force, for the reaction force associated to the constraint is 6D. I have a 3D force and a 3D moment. Okay, and in that case I wouldn't need any force generator matrix. The problem is that writing the frictional constraints with a 6D representation of the reaction force is tricky. It's very tricky. Actually, there is a paper by Stéphane Caron, ICRA 2014, roughly, that went through the math for computing that, and the math is about 2 pages of development. And he only did it for the case of a rectangular shape of the contact surface. If your contact surface is not a rectangle, I'm not aware of any solution for writing exactly the right constraints. So that's bad news. Good news is that there is another possible representation for the reaction forces, that is to say that each vertex of my contact surface shape, I model a 3-dimensional force. And this is an equivalent representation because it allows you to express exactly the same reaction forces in the end. But it's redundant. Because if you have a rectangular shaped foot, you have 3 variables for each vertex, which means you have 12 variables for representing actually a 6D range. So you have twice as many variables than you would need. It's redundant. So one could say, well, why don't I use the same representation for the motion constraint? I can say that each one of the vertices don't move. Yeah, you could do that in theory. But the problem is that if your HQP solver doesn't handle redundant constraints, then you cannot do that. And the HQP solver that we are using in TSID doesn't handle redundant constraints. So we couldn't do that. So what we decided to do was to introduce this force generator matrix that maps from the representation of the contact forces to the representation of the motion space. Okay. So we can use the 6D representation for the motion constraints. So we have a minimal number of constraints that is not redundant. So the solver is happy, and it's also faster. It's a faster problem to solve. We are simplifying the job for the solver, which is always good. But we keep using a redundant 12-dimensional representation for the forces, which simplifies the job for us, because we can write now the friction cone constraints as a collection of 3D friction cones, which is very simple to do. Okay, this is really advanced and detailed stuff that even a lot of people who have been working on TSID for a long time are not completely aware of. I wasn't aware of this until I had to design the library, and I sat down and I started writing down the math. I said, okay, is this tricky, how do we solve this? And I came up with this solution. So if you're not completely cool with that, it's not a big deal. Just beware, there exists this force representation matrix which allows you to have different dimension for the force variable and the motion constraint. Questions?
The foot position, the motion constraint is written like the center of, for example, the foot of the flat foot of a humanoid. In this case, I mean, because you need to.
It can be any frame attached to the foot, and you just say this frame cannot translate and cannot rotate. Doesn't matter where it is because it's 6D. Nicola? There was Nicola.
You could spend a little bit of computation time to build a model as a 6D cone contact, one forever.
Yeah.
It's not changing over time.
So now we're going in even more advanced discussions. You could try to map the constraints from the 12D representation to the 6D representation using polygonal projection techniques, like the one implemented in the library CDD. But you have to add the dependency on another library, and you have to trust that this library works well. And that's not the case for CDD, because from time to time it crashes. So you don't want a library that crashes in your control loop.
But if it's done offline and then we don't really care about computation time, maybe we can write.
If it's done offline, then you need to prefix the location of the contact points. So you can do it for rectangular shapes.
Yeah, one foot.
Yeah. If you already know the shape of your contact surfaces, you can do this computation offline and then just hard code it inside the library.
Yeah.
But this approach is more generic and it works very well in practice.
And on the robot, you recommend to do this one because for publishing TSID, it's clear that the generic version is nice. On the robot, should we do that or should we?
Honestly, I see no disadvantage because we are not. The only thing that we are increasing, well, it's the size of the force variables. So yeah, we are increasing the size of the number of variables, so the Hessian, but it's still very fast. So I don't feel the need to improve that. Yeah?
I have a comment. So you say these forces, which are transferred somehow from the edges of the polygon to some point inside the polygon. Can you choose this point? Or what do you do? Because
it doesn't really matter. I mean, the point you choose it when you fix the Jacobian. So depending on where you put the frame that's associated to the Jacobian, that's the point. And you can put it anywhere as long as it is attached to the foot. That's good.
Because my point is, if you can choose it, and you choose the ZMP point, then the torque disappears. I mean...
Yeah, but you don't know the ZMP until you have chosen the control torques.
So Yeah, okay.
That's a chicken egg problem.
Okay, okay.
Okay. Let's move on. That was the only difficult part of this section. Okay, then we have the inverse dynamics formulation class. As I said before, that's the core class of the whole library, which basically takes all your task and rigid contacts and translates them into a quadratic program. So you have method for adding tasks. When you add a task, you can specify both the weight and the priority. But for the current implementation, the priority can only be 0, which means constraint, or 1, which means cost function. You cannot specify more than 2 levels of prioritization. For the weight, instead, you can go nuts and do whatever you want. You could also test it and see at which point you start having numerical issues. Then you have a method for adding rigid contacts. And you have a method for translating the TSID problem into a quadratic program. Well, that's how a quadratic program is defined. That's not very interesting.
I'm sorry, I got confused in the last part. So basically, I can have the problem with weighted in a weighted form. It's okay, but then I have only one hierarchy. That's what you mean.
In the end, it's only one QP that is solved. It's not a cascade.
Maybe on that, so there is, we don't have a strong hierarchical solver. I think the research was quite active in the beginning of 2010, 2015. I think it's pretty dead now, basically because the problem is hard. But it's also a very standalone problem. So you just have to write a solver. So it's not, you don't need a motion planner, a state estimator, a robot, everything together. You just put a piece of code in MATLAB or in Python, it's going to work. And there is still a piece of research to do there. You could come out with strong numerical methods, either by making more robust the active set method that we started to search, or by going with, I don't know, entire point to complete Lagrangian that might be also possible to solve the hierarchical problem. So there is a nice piece of math and nice research to be done there. Nobody is doing it, but it's an open direction. It would be very useful to the community.
I kind of tend to disagree with Nicolas. I mean, sure, it's missing to be a nice piece of research. I don't think that for application, at least in this context, is very useful because we are using weights since quite a while, and I don't see any wall we are hitting because of the fact we are using only weights.
We always have the same tasks, so always have the same weight, and it's fine. So I agree, for investigating the locomotion problem, it's not necessary. But for manipulation, where you always change the task, tuning the gain, it's really a pain. Really. And even for simple tasks, it's always changing, the context is always changing. There is much more variability, and then your hierarchical solver is very, very useful.
Okay.
Well, we can survive without it. Maybe that's why nobody is researching. I think that's because...
Also because it's hard, yeah. So once you have the HQP, well, you need to use a HQP solver to solve it. You just pass the problem specification and you get the output. So in the output you have the problem variables, the Lagrange multipliers associated to the problem variables. If you don't know what that is, not a problem, just don't care. And you have a flag that's telling you if the problem was solved nicely, or if it was labeled as unbounded or unfeasible, or if there was just an error and the solver could not find a solution. So that's an important flag to check before sending not numbers to your motors. Available HQP solvers. In the library you will find 3 solvers that are available. They're all, none of them supports the hierarchy. and they're all based on the original version of AQuadProg, which is a modified version of the solver uQuadProg++, that was modified to be working with eigenmatrices. Just for you to know, it's a bit of history. So we started from that, AQuadProg, but we were not completely satisfied with the performance, so we've been working a bit on it to make it faster, and we came up with 2 new versions. You have AQuadProg real-time, which is the fastest available, but it works with matrix sizes that are known at compile time. So you have to know before, at compile time, you have to know the size of your problem. So you have to know the number of constraints, the number of degrees of freedom, the number, everything. Instead, otherwise, if you cannot know that at compile time, you can use AQuadProg fast, which is a bit slower, but it allows you to change the size of your optimization problem. So you can add and remove constraints online. So these are the results for the computation time that I got on HRP2's computer, which is a very, very old machine. So you can take them as an upper bound. If you run them on your computer right now, probably there will be half of that. So the average computation time of AQuadProg for the TSID on HRP2 was about 0.7 milliseconds. AQuadProg fast is 0.6, and AQuadProg real time is 0.59. So you don't gain much going from the fast version to the real time version. But in case you need that extra edge, it's there. Okay, so now it's time to start playing with the code. I don't think we have much time left. At what time are we supposed to stop? Anybody knows? 12:30? Okay, so we have half an hour for playing with the codes, which should be okay if you have everything already working. So the examples that you will find in the directory exercises, there are 2 examples, example 1, example 2. They are both working with the robot Romeo. I know that some of you have problems with visualizing Romeo. In that case, you can just replace the path to the URDF file of Romeo with the path to the URDF file of Talos, which was working yesterday with Nicolas' class. So the robot will start with both feet on the ground. Yeah.
If you do that, is the frame name the same, like RT frame name, R
No.
ankle?
Yeah, you're right. You have to change also the parameters corresponding to the frame names. Maybe I can come and help you after.
Okay.
So the idea is that the robot has both feet in rigid contact with the ground, so you have 2 rigid contact constraints. And you want to control the center of mass of the robot for maintaining balance. And you want to control also the joint angles of the robot for stabilizing the posture. And I think it's a very good starting point before moving to more complex scenarios such as blocking. So we can quickly go through the code together. Maybe you can open the file and go through the code while I describe it. So yeah, the first part is just to create the robot wrapper, which needs to know where the URDF file of the robot is. And here, if Romeo is not working, you have to specify another path to another URDF file. In theory, it could be any floating-based robot. So if you have another robot you would like to play with, you can just replace the path to the URDF, and it should work. You will also need to change the name of the frames associated to the contact, because those are most probably different on a different robot. Then you create the inverse dynamics formulation class, which is the one collecting all the tasks and rigid contacts and generating the QP problem. Then you create the contact. So when you create a contact, you have to give it a name, you have to specify the robot wrapper, and here you have to specify the name of the frame. So this is the other parameter that you need to change if you want to use a different robot.
So if we just run the exercise 1, are we supposed to see anything else, or do we have to do the changes first?
No, no, no. Exercise 1, it should be working if you can visualize Romeo.
It's not moving. I can visualize it, but it's not moving. And I have the same normal contact forces for each time step.
Yeah, that's good. That's what's supposed to happen.
Oh, I thought it was supposed to move its center of mass?
No, it's supposed to control. Control doesn't necessarily mean move.
Okay, so you have to...
So it's controlling the center of mass, but in the, say, the starting point is controlling the current position.
Okay.
The first step is going to be to change the reference position so that you will start seeing a motion.
Okay.
So you create the contact, you specify the reference for the contact, saying I want my contact to stay where it is at the starting point. You add the contact to the inverse dynamics formulation class, and you do the same for the other foot. Then for creating a task for the center of mass, it's very simple. You just create an object task COM equality, specify the name and the robot wrapper. You set the gains, KP, KG, and that's it. You add it, you specify the weight. The weight for the center of mass task is 1, if I remember correctly. At the beginning of the script, you have the list of user parameters that you can play with. It should be 1. Then we add a secondary task, because it's less important. It's a joint posture task. Specify the gains, and you add it. And this time W posture should be 10 to the minus 2, minus 3. Something like that, which is sufficiently smaller than 1 to be almost as a hierarchy. Then we create 2 trajectory objects, which are actually representing constant trajectories. So trajectories do not move. Very interesting. And as you can see here, the reference for the center of mass trajectory is set to be equal to the center of mass position that we get through a call of the robot wrapper. So if you want to specify a different reference between this line and this line, you should modify COMREF. So COMREF is a NumPy matrix. You should be familiar with that. So you can simply say COMREF square bracket and then the index equal to something, and this will modify the reference. Maybe it's better if you do plus equal, so it's a relative change. And you can, for instance, move the center of mass a few centimeters to the left or to the right. So X is the forward direction, Y should be the lateral, and Z is the vertical direction. Same for the posture. So for the posture, beware that we only, the postural task only controls the joints, not the floating base. So you should only take the elements of the Q vector from the 7th on. Then we create the QP solver. Nothing fancy here. And then we start a for loop, where at each iteration of the for loop, we update the reference for the COM task and the postural task. We translate the control problem into a QP problem. We solve the QP problem. We retrieve the motor commands from the QP problem. And if we were using a real simulator or a real robot, here we would be sending the motor commands to the robot, right? That's how you typically do control on a real system. However, since here we don't have a serious simulator, we're gonna do a homemade simple simulator just to see some motion. So assuming that everything is perfect, our model is perfect, our torque tracking is perfect, basically the joint accelerations that will be generated by the torques that we computed are exactly the same joint accelerations computed by the QP solver. So we can simply retrieve the accelerations and integrate them. Well, once for the velocities and twice for the configuration. We use the Pinocchio function integrate because in Q we have also the floating base, so the integration is not as simple as this one, but we need to use the exponential now. And then we increase time and we keep looking. So the first thing that I suggested to do is to modify the reference for the center of mass. You could also modify the one for the poster, but the center of mass is more fun. Also because at the end of the script you have some plots appearing that are showing you the center of mass position, velocity, and accelerations. You have the reference versus the real trajectories. So you can see that the center of mass converges to the desired value that you specified.
Is anyone able to run it in real time? Because on my laptop it's about 70 milliseconds per step.
70 milliseconds per step.
For the laser Python.
Okay. Well, you should account that it's a Python code, so you have all the Python operations. When I was talking about 0.5 milliseconds, that's C++ code. So.
I'm not in the VM. I compiled the code, but maybe I
So
compiled it with or something.
you could also check if you compiled all the libraries in release mode. Because if you don't specify release mode when you're compiling, it's a hybrid debug release version that is much slower than release.
Yeah. Okay. Well,
So
I'm just going to change DZ for now.
Yeah. On my machine, maybe I can show you how it looks on my machine.
You could also try to disable the visualization.
Yeah, I we use a number of visualization steps, like the module.
Andrea Del Prete is Pinocchio Michu.
Depends which version of Pinocchio you're using.
I don't know, the one.
It's already
Yeah.
So on my machine, if I run the first exercise, this is how quickly.
Okay, yeah, it's going. Yeah,
It's quite fast.
I think mine is 20 times. So
Okay. So in the slides, there are a few ideas for things you can play with to get acquainted with the library. You can change the gains of the center of mass task and see how that affects the convergence. You can change the weights. For instance, what happens if you start increasing the weight of the postural task? Anybody can guess? Steve, what happens?
Change what weight?
I got you. You weren't listening. If you increase the weight of the postural task, then the difference in importance between center of mass and posture is going to become lower, and this is going to have a negative effect on the tracking of the center of mass task. So we can expect that the center of mass doesn't really reach the desired value, but it stops a bit before. Okay.
So, how do you decide to follow more of the posture that the CRM reference?
Well, for balancing, we know that the CRM is much more important than the posture, so we typically give a much higher weight to the center of mass than the posture. But that's a rule of thumb. There is no exact number that you can put there. In practice, between 10 to the minus 2 to 10 to the minus 3 works quite well. I think on HRP2 I was using 10 to the minus 2. In simulation, you can even go to 10 to the minus 3.
Because when the last time I used TSID, I had a reference trajectory that was avoiding collisions, and TSID obviously does not handle it. And actually, in the end, I was just having the main task was just to follow the reference.
Well, if you have a reference trajectory in joint space, you can just remove the center of mass task and follow only the trajectory. If what you care is about the whole joint configuration.
Oh yeah, because here you just have a posture.
Here you have the posture plus the center of mass.
Yeah. Okay, so it's not the same.
So a fun experiment you could do is to set the reference center of mass outside of the support polygon, like set it 20 centimeters to the side. So the robot cannot stand here, right? And the robot should be falling. So that's thanks to the fact that inside the TSID problem you have the dynamic of the system. So it doesn't allow you to do things that are dynamically inconsistent, even if it's only a simple integration, the simulation. But TSID accounts for the dynamics. If we were using a purely kinematic formulation, you wouldn't get this. The robot would be able to stand even if the center of mass is outside the support polygon to the side.
So for now the center of mass reference is just from the robot data. So CRM ref is robot.crm data.
Yeah, because that's a function that gives you the current position of the center of mass. So if you modify that, you write CRM ref plus equal something, then you're changing the reference, you're moving it to different location, and then the robot should move the center of mass to that position when you start the script.
So for now the center of mass task is actually just to stay wherever you currently
Stay where you are, the postural task is stay where you are, so basically nothing happens.
But luckily the sort of T-pose, the Talos robot, is stable.
Yeah, yeah, the default pose is typically double support, stable configuration.
And otherwise, larger contact forces would be applied. Such
Otherwise, if the initial pose was not stable, the robot would fall. One way you can try that is simply removing one of the two contacts. So the robot assumes that only one foot is in contact, and in that case, it's going to fall on the other side. It's going to try to keep the center of mass where it is, but since it's not possible, it's going to just do the best it can in the least square sense, which is not much better than doing nothing.
Right.
In this
so
case.
it will fall to the side in which we have removed the contact.
Yeah. If you remove the right foot contact, it will fall to the right. So when you've played a bit with exercise 1 and you feel you want more excitement in your life, you can move on to exercise 2, where it's just a slightly modified version of exercise 1, where the reference for the center of mass is a sinusoid, and you can play a bit with the parameters of the sinusoid. You can increase the frequency or the amplitude of the sinusoid. and you can check that if you increase the frequency high enough, the tracking of the center of mass will start being bad, and if you increase it even more, well, the robot will fall. And it may not be completely trivial why that happens. So if you figure it out, tell me, I'm interested.
I could stand on one foot, that's